find the velocity, we found the derivative of our original function, which was negative 0.012 x to the second minus 0.002 x plus 6.59. And after finding the velocity, we found the acceleration, which would be the second derivative of our original function, which was negative 0.024x minus 0.002.
Optimization. So we know what our velocity equation is, and now we are going to maximize our velocity to pinpoint the maximum velocity reached during a 100-yard dash. What is our maximum velocity? First, we found the derivative of our velocity equation, which is also the second derivative of our original function, which is also the acceleration. And we set velocity prime equation equal to 0 and solve for the critical point, x. Here we find that x equals negative 0.83, which in this case is x is t for time, and it equals negative 0.83 seconds. This is where the maximum velocity should be. Now, to prove our findings, we will test our critical number on a number line with -1 and +1 as test numbers. We use these test numbers and do the first derivative test and plug into the first derivative of our original function. After plugging both in, we find that our x values keep increasing until they reach x equals negative 0.83 and start to decrease.
Unit 3 project. Position, velocity, acceleration. The group members are me, Nikki,
Laura,
Holly. Conditions of the sprint and runner. Our runner is an active athlete. Our runner is Holly, by the way. Okay. She didn't have a proper warm-up before sprinting, and she's 6'1". The average height of a female Olympic runner is 5'5", 5'6", so we can assume that her height gives her a disadvantage for speed.
We recorded our data points on a table, and x represents the time in seconds, and then our y represents the yards that we ran. For our graph, we chose the cubic function to represent the data points we have collected. Besides the cubic function, we've also tested the quadratic and linear function. Although all of them are very close and indistinguishable, the cubic function had the closest coefficient of determination.
We have two of our graphs, the velocity over time graph and the velocity over position graph. And you can see the relationship between the velocity and position because the max of the position graph is also the 0 of the velocity graph. Graphs are the acceleration versus position versus time graph and velocity versus acceleration graph.
You don't even have to look at the camera though.
Okay, but can you actually see everything? Is that dark enough? Let me sort of. I'm gonna. I'm not gonna write last names.
Oh, I thought we were all gonna write our name individually.
Oh!
No, wait, just keep writing.
But I stopped!
Just keep going,
Stop!
Let's see, okay.
That would be easier.
Go right. Write something, wait, because it's testing.
Okay.
The group members are me, Nikki,
Laura. No.
Holly.
No.
No, Nikki, please. Conditions of
You
the
have to restart.
So here we recorded on our chart
Try not to say